All right, guys, I'm going to do what I can to talk to you a little bit about cyclohexane. Um, we just got through talking about of different rotational conformations of alkanes. So we were looking down the bond of an alkane, trying to sort out what the different energies are as that bond freely rotates around the single bond. So this is similar property, and unfortunately this is one of those videos where I'm not going to be able to really do this topic full justice, because at the end of the day i I just don't have the tools to show you everything in a recorded video without learning some serious video editing and getting some permissions from other folks, that kind of thing. And so what I want to do is I want to talk about the different conformations of cyclohexane when it comes to being able to think about their lowest energy states. But there's a couple of things that you're going to eventually need to look up on your own in order to get a really good picture of what's going on. And so let's start off with this idea about cyclohexane, and we'll take it for granted that you realize that cyclohexane is not flat. Really quickly, I'll review that, and you need to dig that up a little bit. If you think about ideal bond angles of just geometric shapes like squares and triangles and pentagons and hexagons, you would predict that the pentagon is the closest angle to the ideal bond angle of an sp3 hybridized carbon. And so you might predict that that's the lowest energy, that if you were to do a combustion analysis, and what we'll do is we'll look up the combustion analysis of these different molecules, you'd find that per CH2 group, because if it's a ring, it's all just CH2 groups connected to each other, that at the end of the day, the cyclohexane actually has the lowest heat of combustion, which indicates that it's the most stable per CH2 group. So the first thing to think about, well, why is that? And that's because, well, cyclohexane, cyclopentane, cyclobutane, cycloheptane, they're not flat. They're actually three-dimensional molecules. And so they don't actually maintain a planar shape, and that's why ultimately the cyclohexane is the lowest in energy. So what we do in Organic Chemistry 1 is we spend a lot of time looking at different conformations of cyclohexane in order to understand how substituents affect which conformation exists predominantly. Well, the way we work up to that is we start off with cyclohexane, and we just show you how to do that. Then we add a methyl group, and then we add other groups. And so we're going to learn some new vocabulary words eventually, chair conformations. We're going to learn about 1,3-diaxial strain. And what you're going to be able to do, the goal is that you can draw out both chair conformations of cyclohexane. You can appropriately put all the groups in their locations. And also then you can examine the two chair conformations and decide which ones are lower energy, which ones are higher energy, and so which one would predominate at room temperature. All right, so let's get in. Remember, you're taking it for granted that you know why a cyclohexane isn't flat. So you need to look up combustion analysis of cycloalkanes. You also need to look up a video, I think, to really illustrate what happens with these structures as they go from one ring flip to the other. So my suggestion would be to Google chair interconversion cyclohexane conformation animation. Again, chair interconversion cyclohexane conformation animation. And that'll give you, if you look at YouTube, that'll give you a good quick video that's very thorough, that really shows you not only the three-dimensional structure of the molecule, but how that thing flips from one thing between one chair conformation and the other. So what I'm going to do is I'm going to start right off with how do we draw them, and this is what you sort of need to get at when you practice organic chemistry. So let's go ahead and get into that. All right, so here we are. Remember, if we project it in a flat way, we're talking about a flat hexagon. And these are usually how these structures are going to be presented to you. But your job then is to take this structure and project it in a chair conformation so that you can start to analyze the different groups attached to it. But we're going to start off with cyclohexane. Now, remember, it's a chair conformation, and the reason we call it a chair is because if you kind of squint your eyes, you can kind of imagine that it's a chair that has a seat and a back and a footrest. And so, you know, some folks don't see it right away, but if you look at a few different pictures, you might eventually see why we call it that. So let's take a look at cyclohexane to begin with. And I'm going to really spend some time building up the model so that you can see how that's done and do it on your own. So what I'm going to do is I'm going to start off by drawing some parallel lines. And these parallel lines are going to be just slightly offset from each other. Then what I'm going to do is I'm going to create the back and the footrest, as it were, of the chair by drawing other lines in an angled basis, right, like so. And so in order to draw the other version, remember, it's arbitrary how you start. If I start off with the lines like this, then I'll do the same thing, but I want to have the lines at the opposite angle. So if they're going up and to the right in the left side, then I want to have them going down to the right on the right side. And so I'm going to draw the same sort of projection, though, as I create them. And if you look, you know, my drawings are not particularly, they're not identical. Drawing is not something that I'm great at. There's lots of students that aren't good at drawing. Well, ultimately, what you need to be able to do is figure out a way to do it good enough so that you can see the different bonds. And so once you have this framework, then I start drawing the bonds. Now, as you get really good with this practice, it starts to become second nature on where to put the bonds. But my suggestion is to draw the bonds in the same way every time. That way you are not introducing differences in how you draw the structure, and that might then introduce confusion in your analysis. So I always draw the bonds in the exact same way every time. And I start at the top leftmost corner of each structure drawing the bonds. And so on the left structure, I'll start at the top leftmost structure, and I'll place the axial bond here. Now remember, the reason we call it an axial bond is because if I take, I'm going to actually stop sharing my screen so we can see this a little bit better. If I have the full model of a cyclohexane, let's see if I can orient it in a way that shows you that it's kind of like a chair. And so let me tilt it in, and maybe you can see, here's the backrest, and you know, that's the footrest, and here's your seat. And so this is the chair conformation. And so what we do is we say, well, let's put an axis, a pretend axis, right down the middle, and let's let this thing rotate around the axis. And that way, if we do that, just figuratively, then we can then describe the bonds in a particular way. Notice that the white atoms are are parallel to this axis. The bonds that are attached to green atoms are essentially perpendicular. And so that gives us a way to describe these relative bonds. And the white ones we'll call axial, the ones that stick straight up and straight down. they're axial. And then the ones that are attached to green atoms in this picture or in this conformation, we're going to call those equatorial, because if we're spinning this around this axis, then these things are sort of around the equator. Now, there's an important thing to remember, and this is going to be crucial that you do this and put this in your memory. Take a look at the axial and equatorial bonds. If I were to hold this molecule so that the axial bonds are straight up and down, notice that the axial bonds point both up and they point down. Again, axial bonds point up and down. And now I'm going to rotate it just a little bit so you can see along that bond. Take a look at the equatorial bonds. Even though they're essentially pointing straight out, they also point up and down. And so the point of me saying this and stopping to do this is to let you guys know axial and equatorial does not mean up and down. Axial and equatorial means what are they, bonds parallel or sort of perpendicular to this pretend axis of rotation. Both bonds, axial and equatorial, they both have ones that point up and they both have bonds that point down. And so it's going to be crucial because when you draw the structure and you're looking at a three-dimensional projection on a skeletal structure, you have to interpret the wedges and dashes as up and down, not as axial and equatorial. That sort of just falls into place based on the reality of the situation. So if you've watched the animation, or if you paused the video and took a look at the animation, I want to do another thing before I move back to drawing. Take a careful look of where the white bonds are. The white bonds are, or the white atoms are in the axial position. The green ones are in the equatorial position. Now I'm going to take this model and I'm going to manipulate it so that it does the chair flip. It's a little bit tough with this model because all of the bonds are nice and tight together, but there we go. So now I've got the other chair conformation. And so take a look at what happened, right? So in a chair flip, what bonds were axial become equatorial, right? The white bonds are now equatorial, and the bonds that were axial were equatorial become axial. So take a look. The green ones are now axial. All right, there's one more thing that I want to point out though. Generally in a chair conformation, this is what we're saying. If in a chair conformation, if the bond starts up, remember up doesn't mean axial, it doesn't mean equatorial. It just means in what relative position to this plane does the bond point, up or down, right? This one points down. If it's up, it stays up. And so let's follow this. Well, I'm actually going to switch it out. I'm going to turn this into a red atom just so you can follow it, right? So let's get this thing correctly oriented. There's the chair conformation. The red atom is axial. We're going to reverse, but it's also pointing up. I'm going to reverse the chair conformation. Now the white atoms are axial, but take a look at this red one. The red one still, even though it's equatorial, it's sort of pointing in the up direction versus this one that's pointing in the down direction. So again, if it starts out in the up position, it stays in the up position. If it starts out in the up position, it stays there. If it starts out in the down position, it stays there. And so those are some of the things you're going to have to bring into play when you're drawing these pictures. So let's go back and take a look at the picture we started to draw. All right. And so here's the picture that we're starting to draw. And I remember I said, let's start in the same location every time, in the top left corner. And what that means is I want to draw the bond up. And this is arbitrary, but it's just giving me some way systematic to do it. I'm going to draw it up in the top left corner just because that's the way that is convenient. And because I will, if I follow this system, then I'll draw the correct picture every time. So then if I'm going to do the same thing in the next picture, I want to start in the top left and I want to draw the bond up. Now, before I finish drawing the bonds, I want to make an important point. I also tend to mark this atom and remind myself where that atom goes in the chair flip. So briefly, this part of the chair is going to flip down and this part of the chair is going to flip up. If that's the case, flipping down, flipping up, then it turns out that the green atom is right there. And so I also tend to mark one atom on each structure that is indicative of the same atom so that I can eliminate just a little bit of extra confusion and it helps me organize my thoughts. So going back to drawing the bonds though, up on the left structure, starting at the top left, up on the right structure, starting at the top left, and then we just continue to draw the rest of the axial bonds. Up, down, up, down, up, down. And so let's do it on the other structure. Down, up, down, up, down. Now what I want to do is I want to draw the equatorial bonds. Remember, if the axial bond is up, the equatorial bond is down, and vice versa. So it's fairly easy to do them for 4 of the atoms, but for 2 of the atoms in each of the chair flips, it's important to realize where that projection should be placed. The direction of the bond in the middle of the chair should angle towards the longer of the legs. So this bond is a little bit longer than this bond, and so I'll angle this up but equatorial bond towards it just a little bit. Same thing is true over here. I'll angle it up or down and towards that one. Same thing is true over here. Down and towards that one, up but towards that one. And then let's fill in the rest of them. Here's down, here's up. I'm going to make that a little better. Up. Here, this one is up, this one is down. So down, up, down, up. And so if I were to take, and I'm going to fill in the hydrogens, I'm just going to use blue and red dots for hydrogens in this case, but I want to do them correctly in order to show you that, remember that in the 2 versions, if it's equatorial in one chair, it's axial in the other and vice versa. So I'm just arbitrarily going to start off by using all blue dots in the axial position on the left, and then all red dots in the equatorial position on the left. And then vice versa. So remember that if it's axial, then it becomes equatorial. If it's equatorial, then it becomes axial as the chair flips. And now this provides you with a correct projection of all of the different atoms that are involved in a cyclohexane. So let's just take a look at our green atom again, just so that we can follow along and re-summarize everything that happened. Let's take a look at the blue atom. It's axial on the left, but equatorial on the right. Remember, and that's true, right? Because if it's one in one picture, it'll be the other in the other picture. But something that I want to remind you of is that in the left picture, on the green atom, the blue ball points up. In the right picture, on the green atom, it still points up. If it starts up, it stays up. If it starts down, it stays down. Let's go back to the green atom on the left picture. Let's take a look at the red ball on that atom. That red ball points down, even though, and it's equatorial. When the ring flip occurs, that red ball becomes axial, but it stays in the general down position. And so what I mean by that is to interpret that in each of these cases, there's a hydrogen. And if I use wedges and dashes, then what we do by convention, and this is just convention in my class, is that we call the wedges, the ones that are pointing towards you, we're going to call them up. And the dashes, the ones that are pointing away from you, we're going to call them down. Okay, and so let's take a look at, let's erase this, and let's actually do something. And in this case, I'm not gonna show any particular stereochemistry. I'm not gonna show whether or not this CH3 in this picture is pointing up or down, because it's not important in this particular analysis. So what I wanna do is I wanna move on over, stop talking about cyclohexane, and I wanna start talking about CH3. Or excuse me, methyl cyclohexane. And there's a video about how to name these things. And so take a look at that one to make sure that you are on the same page with me when it comes to naming. All right, so let's take a look at this guy. I'm going to erase the blue ball and I'm going to put the CH3 there. And so I want to make sure that I put it in the correct location on the other chair conformation. So it goes here. So I want to make sure that you understand that in the chair conformations, again, if it's axial, it goes to equatorial. If it starts off up, then it stays up. In this case, I could have used the down one. It doesn't actually matter, because remember, I can take any of these rings and I can flip them over. And so as long as we're consistent in our examination, in this particular case, it doesn't actually matter which way I'm looking at, because in reality, it can be flipped over. Later on, as we get more groups, again, it's not going to matter which way you start, but once you start, you have to stick with that direction and be consistent throughout the entire examination. Otherwise, you start to you end up drawing, if you flip it over in the chair flip, you end up actually drawing the same picture and you get confused. All right, so let's take a look at these two versions. So the first thing I'm going to have you do is have a molecule, and I'm going to give you a skeletal structure like this, and I'm going to say, draw both chairs. And that's what we've done right now. We've drawn both chairs. But then I'm going to say, which conformation is lower in energy? And I'm going to say, and why? Okay, and so this is the next part that you have to do. This is the examination of the structure and to think about what's going on. Okay, so there's a vocabulary word that we need to learn. 1,3 diaxial strain. One of these exhibits this type of steric strain, and steric strain, in a word, just to summarize it, is an increase in energy due to crowding effects, due to the fact that electron clouds don't want to be next to each other. When they're forced to be next to each other, that raises the energy of the molecule. So in other words, steric hindrance, steric strain is caused by crowding of electron clouds, and 1,3 diaxial strain is a particular type of sterics, a steric strain. And so let's take a look. One of these molecules, one of them exists in the vast majority of molecules. It adapts, let me rephrase this. One of these conformations is the conformation that exists at room temperature in the vast majority of molecules, 95%. The other conformation only exists in about 5% of the molecules at room temperature. Now, of course, this is just on average, because remember, the molecule can flip back and forth. But because it's an equilibrium, the lowest energy structure predominates the equilibrium. And in this case, the difference in energy leads to a 95% split in the actual populations of the two molecules. So which one of these things actually is exhibiting the most diaxial strain? Well, it's the one on the left. Why is it the one on the left? What I'm going to do is I'm going to redraw this, and I'm actually going to show it in its three-dimensional arrangement so that we can see that it's a CH3 group. A CH3 group has a bit of an electron cloud, and that electron cloud takes up space. But so do these hydrogens here. And it's much harder to see, but this hydrogen also interacts with that electron cloud. Why is it called 1,3? Well, it's arbitrary. If I were to call the green atom 1, then this would be atom number 2, and this would be atom number 3. Going the other way around the ring, this would be atom number 1, and this would be atom 3. So the interactions that cause an increase in energy are between the groups attached to the first carbon and the groups attached to the third carbon, depending on which way you go around the ring. That's why we call it 1,3 diaxial strain. And so it's much more difficult in these pictures because I'm not a great artist and I can't project it on the fly, but the electron cloud of the CH3 group is interfering with the other electron clouds in the axial position. But let's take a look at what's going on when it's in the equatorial position. When the group is in the equatorial position, the atom sticks out off to the side. And so I'm going to bring back this molecule. So here's the equatorial bond. It's sticking out. And it's not able to interfere as much as with the other molecules. This atom, and let's just say it was an oxygen atom that it's red. Now this is an OH group, but what if it was a CH3 group? Look at how close it comes to the other axial bonds. And so that causes a bit of strain. And this is an illustration of 1,3 diaxial strain in cyclohexanol. This would be the highest energy conformation. Let's do the chair flip. Now that I've got the OH group in the equatorial position, look how much room it's got. It's not nearly as close to the two groups adjacent to it, and it gets to be much lower in energy. And so that leads the conformation on the left for methyl cyclohexane to be much higher energy than the structure on the right. So at the end of the day, what we're saying is the structure on the left has the most diaxial strain, so it's the highest in energy, and that means the structure on the right is the lowest energy. Okay, so let's get closer to wrapping up this demonstration, and let's take a look at a molecule that has more than one substituent. And what I'm going to do is I'm going to actually draw the three-dimensional projections of the different substituents. Your job, and it's easy for me because I'm using electronics, you should pause the video, redraw the framework in your notes, and get ready to draw a completely different structure. So redraw the two different cyclohexane chair conformations, draw all the axial and equatorial bonds, and be ready to put on the different groups. And so I'm actually going to do a little bit of erasing. I'm going to take off the blue and the red, and I'm going to start to replace it with actual groups. And I'll actually replace it with the actual atoms involved instead of being red and blue hydrogens. Okay, so now that you've got this same framework drawn out, let's take a look at a different structure. Let's look at something that might end up being like this: a wedge coming out towards you, and a 1-methyl ethyl or a isopropyl group, whatever you want to call it. Let's go next door and let's put a CH3 going away from you. And let's move 2 spaces over from the CH3. And let's put, coming towards you, let's put an ethyl group, CH3. So that's CH2, CH3. All right, so now we have a much more complicated molecule. And what we need to do, now that we have these two frameworks drawn out, is correctly orient the different groups. So what I'm going to do is I'm going to just start arbitrarily with the CH3 group. And remember, in our class, by convention, I call the dashes that are going away from you, I call them down. And the dashes that are coming, are the wedges that are coming towards you, I call them up. So let's start with the green atom, and let's assign the green atom to the atom that has the CH3. We didn't have to do that. We could do any of the other atoms. It doesn't matter, but we're going to choose it here just to be consistent. Because I've marked the green atom in both structures, I know which atom is the same. And so let's put the CH3 on this atom on the correct bond. And this is where the difference between axial and equatorial comes into play. Is that CH3 group axial or equatorial? Well, the answer is it's both, depending on the conformation. But because of convention, the correct question is it up or down? Because it's a dash, we're going to assign it to the down bond in the left structure, and that means that it goes here. And that means the other thing is a hydrogen. So let's flip it, let's do the other chair, and let's make sure that we have the CH3 group in the correct location. Which one of these bonds does it go on? Does it go on the axial bond or the equatorial bond? Well, in this case, it goes on the axial bond because in the other version, it was on the equatorial bond. Remember, equatorial goes to axial and vice versa when the chair flips. And also, once it starts down, it stays down. The CH3 on the left is in the down position. The CH3 on the right is in the down position. So now I've got my H. I am going to arbitrate. So the next move is to go 1 carbon over. I'm going to go 1 carbon over, and I'm going to go ahead and do it in the clockwise direction. I don't have to do it that way. I can go counterclockwise, but whatever way I choose, I want to be consistent in the next structures. Just to maintain the basic level of consistency and to avoid introducing any extra levels of confusion, since I'm going clockwise in the picture on the top that's flat, in the actual chair conformations, I'm going to go clockwise as well. So this would be clockwise around the ring. And so since I went clockwise in the flat position, I'm going to go clockwise around that ring. Going to go clockwise around the ring. So what's the next atom over clockwise around the ring? Well, if it's this atom, then going clockwise around the ring means that I get to this atom. So now that I'm there, I want to put the isopropyl group in the correct location in order to be consistent with the two drawings. The isopropyl group in the flat projection is in the skeletal structure, it's pointing up because it's on a wedge. So now I have to go to that red dot on the chair conformation and say, well, which one of those atoms is or which one of those bonds is pointing up? Well, the axial bond is the one that's pointing down. The equatorial bond is the one that's pointing up. And so if I were to put my isopropyl group here, I'm correct because that's the bond that points up. Now I want to do the same thing on the other structure. Remember, I'm being consistent. I want to go clockwise around the structure. I want to go clockwise starting from the atom that has the CH3 group. So clockwise around the structure, starting with the atom that has the CH3 group, means that the red atom is here. That's the same atom as the one on the left. Well, where does the isopropyl group go? It was equatorial, now it's axial. It was up, so it stays up. That helps us decide that's where it belongs. Okay, let's continue to go clockwise around the ring. But from the blue one, or from the red one, I want to go 1, 2, 3 spaces clockwise. And that gets me to the ethyl group. So let's do that on the chair conformation. Let's go 1, 2, 3 spaces, continuing to go clockwise around the ring. And remember, it's arbitrary that we're deciding this, but we're being consistent so that we don't introduce any extra degrees of confusion. So 1, 2, 3 spaces around the ring clockwise means we land there. So that's the spot where we want to draw the ethyl group. And so now what we want to do is we want to decide, where does the ethyl group go? Well, it goes up. So that means that the CH3, CH2 group is on this bond. And I'm going to erase that, just draw it a little bit better. And now that I've drawn that, what I'm going to do is I'm going to come back and fill in all the rest of the hydrogens. That way I've got a complete picture for my reader. Now let's do the same thing on the other structure. I want to go 3 spaces around the ring, starting from the red atom in the clockwise direction. So which atom is that going to be? 3 spaces around the ring in the clockwise direction. Well, if I start with the red and I go 1, 2, 3, I end up right there. So let's put the ethyl group in the correct location. It was axial, so now it'll be equatorial. It was up, it'll stay up, so that means this is the bond that it goes on. Oops. So now I'm going to fill in the rest of the hydrogens. And now I've got a complete picture. I've drawn the 2 different chair conformations correctly now. So now that I've drawn them correctly, my job is to decide which one is actually lower in energy. In general, what we're going to do is identify the largest group. In this case, it's the isopropyl group. And we're going to say, well, when is the largest group in the equatorial position? And remember, when it's in the equatorial position, it causes the least amount of diaxial strain. Well, in this structure, in structure A, we have the isopropyl group equatorial and the methyl group equatorial. In structure B, we have the isopropyl group axial and the methyl group axial. In structure A, the ethyl group is axial, and structure B, the ethyl group is equatorial. So because the largest group in B is axial, along with the CH3 group, that causes 1,3 diaxial strain between both the isopropyl group and the CH3 group with the adjacent, with the carbons at the 1,3 position. In the structure A, the only thing that's doing 1,3 diaxial strain is the ethyl group. And so the isopropyl group in combination with the methyl group having 1,3 diaxial strain is more energetic than just the ethyl group doing it. So which one is lower energy? A is lower energy, even though it has ethyl axial. In B, the isopropyl and the methyl are axial, which is more 1,3 diaxial strain than A. Or, yeah. So that's it. That's I know the video went really fast. I know there's a lot of information in that video. I know that I couldn't show you an animation of the ring flip. And so you really are, it really is incumbent on you to go look up that animation. I know that all I could do was show you the model, and the camera and the model don't always sort of coincide and make a really good description of what's going on. But hopefully, if you go back, look up that animation that I asked, look up the information on what I mean by heats of combustion, and then tie that together with this video and the instructions on how to draw the different chair conformations, you should be able to approach any problem. And so what I'm going to do is essentially just like I showed you in that last example. I'm going to give you a flat skeletal structure. It's going to have some three-dimensional projections of cis and trans bonds, and your job will be to correctly draw a ring conformation in one case and the flipped chair in the other case. And then you have to examine the two different structures and decide which one of them actually exhibits more 1,3 diaxial strain than the other. That's going to be your major goal. And if you can do that, then you're done with alkanes and you're ready to move on with stereochemistry. Have a good day, guys.